Tesla Motors engineers made a stunning design choice when they developed the Tesla Model 3. They abandoned the conventionally used and well-proven induction motors and replaced them with a new kind of motor, the IPM Syn RM. These motors have a totally different design, making use of both magnetic and reluctance action. The big news is that Tesla Motors has started replacing the induction motors in their Model S with these new motors as well. How do these motors work? What's so special about the IPM Syn RM? Let's explore. To get a clear answer, we first need to understand the Model S's electric motor, which is an induction motor. Clearly, as you can see, the rotating part here is an arrangement of conducting bars. Alternating currents from the battery packs flow into the motor's outer windings. This will create a rotating magnetic field. The fluctuating field interacts with the rotor bars and generates electromotive forces on them, which in turn generates currents in the rotor bars. The interaction between these induced currents and the RMF imposes force on the rotor bars, and the rotor starts to spin. These motors are efficient, but not up to the mark. For instance, long drives at cruise speed lose 3% to 4% of energy to generate currents in the rotor bars, which is definitely not efficient. Moreover, for an automobile, the most crucial performance parameter is its starting torque. Even though the induction motors have a better starting torque than IC engines, there is a motor technology that provides even better starting torque from the same motor volume, a motor technology based on permanent magnets. The PM motors work on the basis of the attraction between two magnetic fields. They produce a good starting torque when you operate them using a controller, and they do not experience energy loss in the rotor. An efficient permanent magnet rotor can be made by placing permanent magnets around a solid iron cylinder. So why not replace the squirrel cage type rotor with a permanent magnet one? These 4 permanent magnets produce a combined magnetic field. The shape of this combined field is quite important for further analysis. With a little intuition, the combined magnetic field of these 4 magnets can be plotted, as shown. Now, we need to analyze the interaction between the RMF and the combined magnetic field. Analyzing force interaction between two magnetic fields is simple. Just observe how the south and north poles interact with each other. For simplification, let's hide the magnetic field produced by the permanent magnets and keep only the north and south poles. The force interactions between the different poles are shown here. At this angle, the RMF definitely produces a torque on the rotor. Now, let's rotate the RMF to 45 degrees. Interestingly, at this angle, the rotor experiences maximum torque because the attractive and repulsive forces are passing almost tangential to the rotor, and they are producing the torques in the same direction. Using this simple ball analogy, the reason behind why tangential forces produce maximum torque is clear. Thus, this is the perfect angle to start your electric car. Maintaining this angle or further angle regulation is the smart controller's job. In this design, the rotor has no induced current, which reduces the input energy required and leads to higher efficiencies than those of induction motors. Along with higher starting torque, the PM motor also runs at synchronous speeds. But the search for the perfect electric motor is not over yet. A permanent magnet motor produces good torque when you start the car or ride up a hill. However, when the car cruises down the road at high speeds, permanent magnet motors have terrible performance. The villain here is the back EMF. The magnetic field lines produced by the permanent magnets link with the stator windings and generate an EMF there. This EMF is called back EMF, which is clearly a reverse voltage to the stator's supply voltage. The higher the rotor speed, the more it produces back EMF. This phenomenon is why the permanent motors perform terribly in high-speed applications. Moreover, these high-strength magnets also result in magnetic eddy current losses, which increases the heat in the machine. Let's see how we can modify this design so that it will work efficiently even at high speeds. For high-speed operation, Tesla engineers made use of iron's reluctance property. A medium's ability to oppose magnetic fields is known as reluctance. An iron nail sticks to a permanent magnet due to the reluctance force. Iron is a good keeper of magnetic field lines, but air is not. An interesting phenomenon can be observed when slots are cut in the iron. At this rotor position, the rotor is in a high reluctance state. However, if the rotor is turned by 45 degrees, it will face a very low reluctance. The rotor always has a tendency to attain a low reluctance state. Therefore, if the magnetic field rotates, the rotor will rotate along with it, so that the rotor can always be in a low reluctance state. The rotor's rotation speed will be the same as the RMF speed. The torque produced by this phenomenon is known as reluctance torque, and such motors are called synchronous reluctance motors. Syn RMs are highly efficient and they don't have back EMF issues. In short, permanent magnet motors are good at low speeds and Syn RMs are quite good for high-speed operations. If we can integrate the Syn RM technology into the permanent magnet motor we saw earlier, such a motor could work efficiently at any speed, a motor which utilizes both reluctance and permanent magnet effects. We can easily achieve this design integration by placing the permanent magnets into the slotted cuts of the Syn RM motor, deep within the iron core. This placement further reduces the magnet's effect on stator winding and thus reduces back EMF. This design is the internal permanent magnet synchronous reluctance motor, or the Tesla Model 3 motor. The relative permeability of the magnets is almost the same as that of the air, so they will oppose the field to pass through it, just as the air did earlier, thereby generating the reluctance torque. To analyze this motor properly, we first need to observe the resultant magnetic field that the permanent magnet arrangement produces. The FEA software EMWorks 2D, paired along SolidWorks, comes to the rescue. The resultant magnetic field produced by this arrangement will be as shown. If these magnets were placed far apart, each magnet would create its own magnetic field as shown in the left image. Using this resultant field, let's do the further analysis. The interesting thing about this design is that the permanent magnet and reluctance parts of this motor have totally different behavior in regard to the position of the RMF. Let's analyze them separately. From our latest IPM Syn RM design, remove the iron core and keep only the permanent magnets. At this RMF position, the permanent magnets will not experience torque, as there is no tangential component for these four forces, and the torque the remaining forces produce cancel each other out. If the RMF is rotated by 45 degrees, a torque acts upon the magnets in a clockwise direction due to the effect of the RMF. At this angle, we get maximum torque out of permanent magnets. Let's see what happens when we turn it by another 45 degrees. The torque the rotor produces goes to zero again, allowing us to obtain the permanent magnet's torque curve. The iron part of the rotor has an opposite effect on the same technique. Let's analyze it. At the initial angle, the torque production will be zero because it's a perfectly misaligned and symmetrical case. When we slightly offset the RMF in a clockwise direction, the rotor will experience a negative and maximum torque. As the RMF reaches 45 degrees, the torque becomes zero again, since this is a perfectly symmetrical case again. As we further rotate the RMF, the reluctance torque produced will be positive. Now let's analyze the Tesla Model 3's motor or the combined permanent magnetic and reluctance effect together on the motor. It's clear from the total torque graph that if the RMF angle is around 50 degrees, we'll get maximum torque from the motor. So Tesla Motors engineers made sure that when you start the car, the RMF angle is around 50 degrees, which will guarantee maximum torque production. We know that as the motor speed increases, the permanent magnets induce a back EMF on the stator coils. To overcome this issue, Tesla Motors engineered a solution that is quite simple for turning at high speeds. They aligned the RMF opposite to the permanent magnetic field. As you can see, the RMF weakens or almost cancels the permanent magnet field. This way, even at high speeds, such motors won't produce much back EMF. Obviously, at this stage, the torque production will mostly come from the reluctance effect. Model 3 uses a 6-pole design, which is no different than a 4-pole design, apart from getting higher torque. Tesla Motors is not the first company to release such an innovative motor. The Toyota Prius, a hybrid electric car, uses similar IPM SynRM motor technology. It uses 2 IPM SynRM machines, one for motoring the car and another for generating electricity. An interesting difference between the Model 3 and Prius motor designs is in the magnets. Prius motors use solid magnets, whereas each magnet in Model 3 motors is segmented into 4 parts. This segmentation reduces the eddy currents in the magnets, preventing them from overheating, which in turn saves them from demagnetization and runs the motor cooler. The 2019 version of the Model S cars have IPM SynRM fitted at the front. The IPM SynRM motor has efficiencies of up to 96% compared to the traditional induction motors of up to 94% efficiency. Effective cooling of an induction motor's rotor is a big challenge. This issue is not present for IPM SynRMs. With the added advantage of reluctance, these motors have higher torque values than induction motors. IPM SynRMs have definitely set new standards in the EV world. We hope you enjoyed this explanation of how clever design decisions gave birth to a promising electric motor. Don't forget to be one of our supporters. Thank you.